This is my biomechanical analysis of a sprint start by Ryley. So the sprint start from the blocks plays a pivotal role in the Olympic track and field events, such as the 100-metre, 200-metre and 400-metre sprints. The sprint start is where the most significant change in velocity occurs as athletes strive to accelerate rapidly and generate maximum force. The sprint start commences with the starting commands of on your marks and set with distinct body positions. Once all sprinters assume their set position, creating pre-tension through the legs on the block until the starter's gun marks the official start of the race. The athlete's primary objective at the initiation of the sprint is to achieve maximum acceleration by increasing horizontal velocity and thus generating the greatest force. Acceleration is greatly influenced by several factors such as inter-block spacing, the positioning of various body segments, including the trunk, front and rear legs, hips, knees and ankles, center of mass during the set and first flight phase. These adjustments enable a wide range of joint extension, increasing the horizontal force production whilst leaving the blocks. To optimize the sprint start performance, the athlete uses propulsive forces against the starting block to propel their body forward in a horizontal direction. This is my deterministic model, and it was developed to identify the most critical biomechanical principles to achieve the goal of the sprint start, which was the maximum horizontal force. And upon completion, the analysis allowed for the identification of 4 features that were the most important for critical quantitative and qualitative analysis. In order to capture the essential positions of the set block phase and the initial takeoff stride following the push-off phase, the university provided an iPad which allowed for slow motion filming at a frame rate of 120 frames per second. The iPad was strategically positioned 5 meters from the performer, placed at a 90-degree angle to the set block and track field. It captured footage from the left side, focusing on the sagittal plane as this was the performer's dominant foot for initial contact. Filming took place outside to ensure optimal lighting conditions, and the location choice helped to avoid distracting background elements or other individuals within the frame. The participant performing the skill received instructions to wear clothing that was suitable for performing the sprint start comfortably and was guided on how to execute the skills correctly, including adopting the general appropriate on your mark and set and go positions. Additionally, colored markers that contrasted with the participants' clothing were affixed to enhance visual tracking and analysis. The markers were placed along the left side of the participant's body laterally, including the radiocarpal joint of the wrist, the glenohumeral joint of the shoulder, the hip articulation, kneecap, and talocrural joint of the ankle. First critical feature identified was horizontal velocity. This was primarily because it allowed the sprinters to achieve maximum acceleration quickly. An initial increased horizontal velocity enables the sprinters to accelerate rapidly and gain an early advantage within their sprint event. So impulse, which results from the application of force over time, facilitates a larger horizontal velocity. Ultimately, the larger horizontal velocity will therefore benefit the athlete. Skilled sprinters tend to have a smaller takeoff horizontal velocity which decreases during the first ground contact, enabling them to generate the highest amount of force. Research showed that skilled sprinters have reported mean values of approximately 5.7 meters per second for horizontal velocity from the stationary set position to the first initial stride at toe off of the second post-block step. From the observed footage, raw data for calculating velocity was determined using the formula velocity is equal to the change in displacement divided by the change in time. From the footage using the Canova app, I calibrated centimeter measurement with the use of a 1 meter ruler and therefore calculated the displacement of the participant's center of mass from the toe off of the second post-block step. The calculated horizontal velocity was found to be 2.7 meters per second, which is a 3 meter per second difference, but this data is in comparison of a normative participant and an elite performer. So, in order to further advance the performance and achieve the desired goal of maximum force in the sprint start, the following recommendations for corrections can be implemented. This includes increasing the flexion of the body segments by encouraging the participant to increase the flexion of the angle of body segments, especially through the knees and the hips. This will develop concentric strength of the hip and leg extensors to increase the ground reaction forces and propel them from the starting blocks at a desired velocity and force. A second recommendation can be to ensure that the participant optimizes the transfer of angular momentum achieved by focusing on the body position during the sprint start. By implementing these recommendations, the participant can improve efficient transfer of angular momentum, increasing the horizontal velocity and maximum force production. I also found the center of mass to be a crucial biomechanical parameter that plays a pivotal role in understanding the body position and segment movements during various activities. So the lowering of the center of mass is instrumental in enabling performers to generate impulse, which in turn results in achieving a larger horizontal takeoff velocity and greater horizontal displacement. According to the research of Schutt and Knudsen, the optimal set position for block velocity was determined by a horizontal distance of the total body center of mass from the start line, which they found to be 32 centimeters. However, from the footage analysis, in this case showed that the center of mass from the start line was approximately 50 centimeters. So this difference led to a decrease in the force impulse in the starting block and less efficient block acceleration. The total body center of mass is important in the first two post-block steps, so positioning the total body center of mass ahead of the contacting foot encourages an increase in horizontal force production. Within my analysis, it is evident that the participant's total body center of mass is not placed anteriorly to the foot contacting the ground. So to fix this, the following recommendations for corrections can be implemented. These include adjusting the body's positioning to create the center of mass anterior to the first foot contact on the ground. This can be achieved by bringing forward the trunk lean and increasing the angle of the hip flexion of the dominant front leg. We can recognize that the individual center of mass is mainly dependent on the performer's anthropometric characteristics and their motor ability. Therefore, it is recommended to discover the preferred set position based on the sensation and desired outcome. In order to decrease the horizontal distance of the center of mass to the start line, we can instruct the participant to distribute the body mass evenly between the legs and arms while adopting a forward trunk lead and hip alignment. This adjustment will lower the center of mass to generate impulse and increase the horizontal takeoff velocity, thereby leading to a desired maximal force for the sprint start. So during the push-off phase of the sprint start, the performer will strategically utilize the positioning of the lower extremity to optimize the ground reaction forces whilst propelling themselves forward off the starting block. The key biomechanical principle is the coordination of the hip, knee, and ankle to achieve a triple lower extremity straightening, which is essential for an efficient transfer of the ground reaction forces. This in turn leads to a generation of a reaction that propels the body forward, a fundamental concept for producing maximal force and power to enhance the sprint performance. Proper hip straightening is a critical element in this process as it ensures the power generated from the hips is effectively transferred to the ground. By combining a lowered center of mass and straightening of the hip extensor, knee extensor, and plantar flexion of the ankle joint, athletes can optimize their technique. This will minimize any unnecessary movements and allows for the greater range of joint extension, resulting in greater velocity when leaving the blocks. Ultimately, this will prevent premature injury and efficient transfer of horizontal force in the forward motion. So the medium to high hip position within the set position enables a more forceful thrust against the front block, and additionally the knee straightening of the rear leg commences just after the rear block exit and first touchdown, facilitating the transfer of power down the leg. Research findings suggest that the more skilled sprinters place their hip extensor muscles on a greater stretch in the set position, thereby gaining a greater force output from the hip extensor due to the length-tension relationship. In this footage analysis, the purple line represents the trajectory of the rear lower extremity, highlighting the use of the triple extension following the exit from the block. Identifying the faults of this skill includes the limited ground contact time. This can therefore be increased by technique work. Participant can focus on the technique with proper mechanics in the push-off phase. With use of video feedback and consistency can be inherited to correct the triple lower extremity positioning. This increases the linear ground reaction forces, contributing to the increase of momentum and overall improvement in the sprint performance, achieving a maximal horizontal force. To the block provided, the participant without instruction positioned themselves within the starting blocks and adopted a medium spacing into block foot placement. This is a natural postural adaptation of the sprinter modified by the block adjustment. Interblock spacing of the medium block inspired the best start performance, including the position of the hips raised high that enabled the performer to use extensor reflex muscle groups relevant to the sprint, producing the fastest acceleration with the powerful thrust and quick lower extremity recovery. In the work of Slither, Seth, and Grenadier, every sprint race distance was completed in significantly less time from the medium starting blocks than either a bunched or elongated position. However, Work by Slowinski showed otherwise, and the recommended correction to enhance the sprinter's performance in relation to the interblock foot spacing include adopting the elongated start, which induces an increase of the velocity at the block clearance, as it was linked to an increase of pushing time on the blocks to increase the ground reaction forces. In order to improve performer efficiency from the starting block, specific exercises that increase the explosiveness of extensor muscles in the trunk and flexor muscles of the hips can be included in the training programs. This is my reference list, and thank you for listening.